This morning we have Dr. Hugh Ross with us. Dr. Hugh Ross. Let me introduce Dr. Hugh Ross for us. Dr. Ross, astronomer and best-selling author Hugh Ross, travels the globe speaking on advancing scientific discoveries, including those pertaining to cosmology and the study of the origins of matter and life. Intrigued by astronomy from childhood, Ross became the youngest ever director of observations for Vancouver's Royal Astronomical Society at age 16. He completed his BS in physics at the University of British Columbia and MS and PhD in astronomy at the University of Toronto. For postdoctoral studies, the National Research Council of Canada sent him to the California Institute of Technology, where he researched galaxies and quasars. Ross is a popular speaker and has lectured at hundreds of university campuses, conferences, and churches around the world, interacting with people of all backgrounds. In 2012, Ross, together with Dr. Gerald Schroeder, received the Ide P. Trotter Prize presented by Texas A&M University in recognition of his work demonstrating connections between science and religion. After Big Bang cosmology convinced him of a creator's existence, Ross's curiosity led him to examine the sacred texts of world religions for scientific and historical accuracy. Being convinced of the Bible's unique compatibility with scientific and historic data, he recognized how his scholarly scientific background and faith convictions served as a provocative stimulus to dialogue with others in academic and civic environments. Dr. Ross lives in Southern California with his wife, Kathy, and they have 2 sons. Let's give a warm welcome to Dr. Hugh Ross.
Thank you. Well, thank you. And I was raised in British Columbia. I get back there every summer to do some hiking and climbing. This is where we were just a summer ago. And I'm the founder and president of Reasons to Believe, and we do believe in social media. I answer questions that I get on both my Facebook and Twitter page, so if you don't get to ask your question today, you can do that through social media. And we maintain a 24/7 YouTube channel, so you can watch our lectures, our courses, by going to the Reasons to Believe YouTube channel. You can also contact me by texting my name to 31996. That's your portal to get free videos, book chapters, and much more. And we are giving away a free chapter of my best-selling book, The Creator and the Cosmos. You go to reasons.org/Ross, and we're giving away the chapter that pertains to the cosmology of Stephen Hawking and Roger Penrose. And I'm speaking on Improbable Planet today, and we're giving away a free chapter of that book as well. Again, you can get that at reasons.org/Ross. But what I'm going to talk about is what needs to happen in order to make our universe habitable, our galaxy cluster habitable, our galaxy habitable, and our planet habitable. And not just habitable for life, but habitable for human beings, or the equivalent of human beings, and not just habitable for a few hundred of us, but habitable for billions of us. What does it take? And in my book, Improbable Planet, I describe several hundred different features of our galaxy and our planet that must be fine-tuned in order for billions of us humans to live in this planet at one time. Now, as an astronomer, I can tell you there are tens of thousands of clusters of galaxies in our universe, and life is only possible in a cluster of galaxies. But most galaxies do exist in a cluster of galaxies. And your typical cluster of galaxies has anywhere from 1,000 to 10,000 member galaxies. And they tend to be rather densely clustered, and where the cluster is dominated by supergiant galaxies. And just this past Wednesday, astronomers imaged for the first time the event horizon of a black hole. And they chose on purpose a supergiant galaxy at the center of the Virgo cluster of galaxies, M87, because its black hole comes in at 7 billion times the mass of our star, the Sun. And if you didn't get to see that image, I've got it posted on my Facebook page and my Twitter page. First ever image of the event horizon of a black hole. But this is what our cluster of galaxies looks like. It's not at all like a typical cluster. It doesn't have thousands of galaxies. It's only got about 100 galaxies in it. It has no giant galaxies. It's the only galaxy cluster I'm aware of that doesn't have a giant galaxy in it. Instead, it's got two large galaxies, our Milky Way galaxy down at the lower right, and the Andromeda galaxy at the upper left. All the rest of the galaxies are dwarf galaxies. And notice they're far apart. A typical cluster of galaxies, the galaxies are about this far apart. Ours are much farther apart. And because they're farther apart, you don't have the structure of the Andromeda galaxy or a Milky Way galaxy heavily distorted, as is typical in other clusters of galaxies. On the other hand, the spiral structure of our Milky Way galaxy cannot be sustained unless our Milky Way galaxy is consuming dwarf galaxies on a regular basis. Our Milky Way galaxy has a diet of these tiny galaxies that it sucks into its core, and the gas of those small galaxies that it's consuming sustains the spiral structure. And life is only possible in a spiral galaxy. Only in a spiral galaxy are stars far enough apart from one another where you can actually have life being sustained on a planet that's orbiting it. But the other unique feature of our Milky Way galaxy is that it's got 2 of the 5 largest galaxies. In fact, the largest dwarf galaxies in our local group of galaxies are the small and large Magellanic Clouds that are imaged up at the top of this picture, and they're positioned in such a way that they act as a gravitational funnel to draw in smaller dwarf galaxies into the center of our Milky Way galaxy, and explains why our Milky Way galaxy has had such beautifully symmetrical spiral arms for the past 10 billion years. And that little yellow dot there shows you the position of our solar system, and right now we're halfway between 2 spiral arms. That's a good place to be. An article got published just yesterday in the Astrophysical Journal making the point that when we cross a spiral arm, that's deadly for advanced life. It's okay if you're a microbe, but not good if you're an advanced animal. But fortunately, we only cross a spiral arm about once every billion years. And right now, we're precisely halfway between the Sagittarius and Perseus spiral arms. But this symmetrical spiral arm structure, where the spiral arms are far apart from one another, is a unique feature of our Milky Way galaxy. Now, we astronomers have been looking for galaxies far, far away that might be candidates for life to exist. I mean, you've probably seen one or more of those Star Wars movies, and they always open up with a galaxy far, far away. Well, we've looked at galaxies far, far away in the search for a galaxy that's sufficiently like ours that it could be a candidate for advanced life. And bottom line is they need to change the script. There are no galaxies far, far away that have the characteristics that would make possible advanced life. If you want advanced life, it's got to be inside our spiral galaxy. And to show you this, the next 10 slides are the galaxies that we've found that are the most similar to our Milky Way galaxy. But each one of them has characteristics that would rule out the possibility of advanced life. This is the nearest large spiral galaxies to ours, the Andromeda galaxy. But you can see that the spiral arms have been warped and distorted. And that's because there was a recent encounter with a large dwarf galaxy that passed through virtually the center of the Andromeda galaxy. The spiral arms are closer together and warped, and you see there's a lot of feathers and the spurs between the spiral arms. And you do have to be living in a spiral galaxy that's got a bar, but here the bar is way too large, and the large size of the bar has distorted the spiral arm structure. Here's another barred galaxy, and again you can see that in between the spiral arms, you just have dozens and dozens of these spurs and feathers. This is the pinwheel galaxy, often referred to by astronomers as the closest twin to our Milky Way galaxy. But here again, you can see the spiral arm structure is distorted with lots of feathers and spurs in between. There really is no safe place for advanced life in this galaxy. Here's another example, NGC 908, and the outer spiral arms have been severely distorted. M83, and this one shows you how there's just stars all the way in between the spiral arm structure. And here's a couple of more galaxies. These are all the galaxies that are most similar to ours. But this is what our galaxy looks like. Incidentally, this is not a photograph. There's no way we can send a spaceship above our Milky Way galaxy and look back. But this is a map that's been developed by radio astronomers, X-ray astronomers, infrared astronomers, optical astronomers, where we've been able to piece together different sections. And this is really quite an accurate picture of what our Milky Way galaxy looks like. Now, we are aware, because of the composition of our solar system, that our solar system must have had its birthplace in a giant molecular cloud that led to the formation of at least 10,000 stars. So we were born in a dense star cluster. And you say, how do you know that? Only if we were born in such a dense star cluster would we have been blasted by aluminum-26. So aluminum-26 is a short-lived radiometric isotope. And because we were born near to these supergiant stars that produce huge amounts of this aluminum-26 gas being blasted off, that got rid of most of our water and atmosphere. And why is that important? A typical rocky planet the size of the Earth will have 2,400 times as much nitrogen as our planet does, 1,200 times as much carbon, 1,000 times as much water, which means you're going to have a planet with oceans that are thousands of miles deep. And on such a planet, you're not going to have surface continents. You're only going to have water. Or you're going to have an atmosphere so thick that it's going to be impossible for lungs to function. For lungs to be able to function, you want an air pressure that's no more than 3 times what we have here on our planet, or 3 times less. We actually have the optimal atmospheric pressure and the atmospheric composition. But it's only possible if we're born in a star cluster where all the volatiles, the gases in the water, get blasted away by this intense radiation. The other thing we notice about our planet Earth, we are the uranium-thorium champion of the universe. Compared to other Earth-like rocky planets, we have 630 times as much thorium and 340 times as much uranium. Now you say, that doesn't sound nice. Those are deadly radiometric isotopes. They're long-lived radiometric isotopes, and it's because our planet is so super endowed with uranium and thorium, we have this powerful dynamo in the core of our Earth, which generates a strong, long-lasting magnetic field. And that's what protects life from deadly cosmic radiation. It also prevents our atmosphere from being sputtered away by the radiation from the sun. And that uranium and thorium is also responsible for generating the continents. Without that uranium and thorium, our planet would have remained a water world. And so as the molecular cloud begins to condense and form stars, this is a little bit like what the cluster we were born in, but we didn't stay there. What happened was, early in the history of our star, we got gravitationally bounced by nearby big stars, which basically kicked us out of the star cluster. And so we now recognize is our birth spot was the place where the abundance of heavy elements was the highest, and we got sent out to one of the places where it is the lowest. And so that first dotted line that you see there represents the place where we were born. So we were born at this location relative to the center of our galaxy. We got kicked out by a gravitational spark from nearby giant stars, and we wound up stopping in this location here. Now, this is the most dangerous place in our galaxy for advanced life. This is the safest place. So we were born in the most dangerous place. It was important, though, because only if we were born there will we've actually gotten the heavy elements that we need to make advanced life possible. But it's critical we not stay there. Advanced life would not be able to survive there, but we wound up being situated in a place where the star density is low, and it's also the location that is known as the co-rotation distance from the center of our galaxy. Now, the spiral structure you see there basically is a rigid rotating system. It's created by density waves. I won't go into the technical details. And stars revolve around the center of the galaxy according to Newtonian mechanics, which means stars near the center will go around the center of the galaxy rapidly, and those far away much more slowly. This red line here is the co-rotation distance. That's the distance from the center of the galaxy where a star will revolve around the center of the galaxy at the same rate that the spiral structure rotates, which means that's the place where you're going to cross spiral arms least frequently. Now, if you're exactly at the co-rotation distance, you're going to experience mean motion resonances, which will strongly bounce you in or out. Where we are is that just inside the co-rotation distance. We don't experience these destructive resonances, but it means that we cross spiral arms least frequently of any star in the planetary system. We cross about once every billion years. And the last time we crossed was about 500 million years ago, which explains why right now we're halfway between spiral arms. So this indicates the place where we were born, and this indicates the place where we are right now, between these two spiral arms. Now, that's referred to as the galactic habitable zone, the distance from the center of our galaxy where life is possible. Life's not possible here, it's not possible there, it's only possible just inside those co-rotation distance. But when it comes to habitability, when you read the astronomical literature, most of the focus is not on the galactic habitable zone. In fact, I just wrote an article a week ago. Every week I put out an article called Today's New Reason to Believe. And it's posted on our website where I talked about the supergalactic habitable zone. And again, this black hole that was imaged and published just this past Wednesday, that's at the center of the Virgo cluster of galaxies. If we were in the Virgo cluster, then we would not be, that radiation from that black hole would kill us. Our little cluster of galaxies orbits at the extreme outer fringe of the Virgo supercluster of galaxies. We're far enough away where the radiation from that black hole is not strong enough to kill us. And so there's a supergalactic habitable zone, there's a galactic habitable zone, but most of the attention in the scientific literature has been focused on the circumstellar habitable zone, the distance from a star where life might be conceivable. And what we see here is what's referred to as the liquid water habitable zone, the distance from a star where the temperature will be between 0 and 100 degrees centigrade, where water could exist in a liquid form. But again, as you look at the literature, we now realize all the attention has been given to the liquid water habitable zone, but there's actually 10 other habitable zones. So in addition to the liquid water habitable zone, you got the ultraviolet habitable zone, the photosynthetic habitable zone, the tropospheric ozone habitable zone. And I'll go through each of these in detail. One of them was discovered literally just a week ago, and I haven't had a chance to update my slides, so you're only going to get 10 of the 11. But again, you can see today's new reason to believe, where I wrote about the 11th that was just discovered days ago. But again, most of the attention has been focused on the liquid water habitable zone, but there are different liquid water habitable zones. The ephemeral water zone, this is referred to as the possibility of a planet having liquid water on, say, a square kilometer of its surface for maybe a couple of months. And we now realize that's not going to be appropriate for life. If all you got is liquid water for a short period of time on a small region of the planet, then that's going to be of no benefit for life. But this is often the habitable zone that you see referred to in the scientific literature. Then there's what's called the semi-permanent liquid water habitable zone. And this is where we're talking about water existing not just for a few weeks, for a few months, but literally existing for a few centuries. And not just on 1 square kilometer of the planet's surface, but in addition to more than 1,000 square kilometers. And what you notice is, in that case, that zone is narrower. Incidentally, that AU refers to the distance that our planet Earth is from our star. But if you really want to have water that lasts long enough and covers enough of the surface of the planet where life actually can survive, then we're dealing with what's called the permanent water habitable zone. And you can see here it's much, much narrower than what we see typically referred to in the scientific literature. So often what you see in the literature is you have this ephemeral liquid water habitable zone where virtually every planet would be classified as being potentially habitable. In fact, if you go to the NASA website, they refer to the fact that there could be 40 billion habitable planets in our Milky Way galaxy. But they're referring to this habitable zone, where you got this very broad, but again, if all you got is liquid water in a square kilometer for a few weeks, that's really not a habitable planet. If you really want to have the possibility of life, you need the water to hang around for a while, and it needs to cover a significant fraction of the planet's surface. And so in terms of a permanent liquid water habitable zone, this is what it looks like. And incidentally, this has been exaggerated so that you can see it in this audience. The next slide actually shows you what this permanent liquid water habitable zone really does look like. You can barely see. And our planet Earth does exist in that permanent liquid water habitable zone. Now, the other habitable zone that's gotten the most attention in the scientific literature is what's referred to as the ultraviolet habitable zone. And the recognition is if you got too much ultraviolet radiation coming into the surface of your planet, that will kill life. But you need at least a little bit to come in because you need some ultraviolet radiation, particularly the longer wavelength radiation, to synthesize critical biochemicals. So without ultraviolet radiation, life is impossible, but too much ultraviolet radiation makes life impossible. But what astronomers have been able to determine is that if a star is less massive than the sun, then the ultraviolet habitable zone does not overlap the liquid water habitable zone. For life to actually exist, both zones must overlap one another. And for stars more massive than the sun, we discover that the ultraviolet habitable zone is outside the liquid water habitable zone, as opposed to what we see with stars that are less massive. Now, just simply recognizing that for a star or planet to be truly habitable, we must have both the liquid water and ultraviolet habitable zones overlapping. That eliminates all stars that are younger than the sun and eliminates all stars that are less massive than the sun or more massive than the sun. Suddenly that 40 billion drops down to just a few million. But what we recognize is that if life is not photosynthetic, it doesn't do much. The metabolic rates for photosynthetic life are 1,000 to 10 million times higher than for non-photosynthetic life. And if you want any kind of advanced life, you have to begin with photosynthetic life. In fact, the amazing thing is the origin of life on planet Earth was not just the simplest microbes, it included the more complex microbes, including 2 different kinds of photosynthetic microbes. But it's only the photosynthetic life forms that actually have a metabolic rate high enough where you can actually have a diversity of life that's adaptable enough that life can actually survive for a significant period of time. And what we discover here is that the ultraviolet habitable zone is much narrower than what I showed you in the previous slides, and it requires much higher stability in that ultraviolet habitable zone. Now, I've given you 3 habitable zones. Of all the planets we discovered, it's almost 4,000 planets we've discovered outside of our solar system. Of those 4,000 planets, how many reside in the liquid water habitable zone, the ultraviolet habitable zone, and the photosynthetic habitable zone? The answer is 0. We've yet to find one that resides in those 3 zones. But you also have to reside in what's called the tropospheric ozone habitable zone, where you have to be the appropriate distance from the star, the host star, where you got enough ozone to make sure you don't get the buildup of biochemical smog. For example, trees pour out a lot of smog, grasses pour out a lot of smog. But it's tropospheric ozone that prevents that smog from building up to a level where it's deadly to all life. But too much ozone means you're not going to be able to have animal life. And even certain kinds of plants would experience problem respiring if the ozone level is too high. And then we have what's called the planet rotation rate. That actually changes these different zones because it affects the cloud reflectivity. And the faster it rotates, the warmer the planet is, and that could push it in or outside of the habitable zone. Likewise, the tilt of a planet's rotation axis, the higher the obliquity, the warmer the planet, and that could change the habitable zones. Another zone that's gotten a lot of attention was called the tidal habitable zone. And the whole point here is if you're too close to your star, you get tidal locking. If you want an example of tidal locking, think of our moon. Our moon is sufficiently close to the Earth that the gravitational pull of the Earth on the near side of the moon is quite a bit stronger than is on the far side of the moon, and this forces the moon to maintain one face throughout its entire revolution. Basically, tidal locking is defined where you got enough tidal forces that it means that the rotation rate of the planet becomes identical to its revolutionary rate. Now, for example, both Venus and Mercury are sufficiently close to our star, the Sun, that they've experienced tidal locking, where they have rotation periods that are quite similar to the revolutionary period. Consequently, it's blazingly hot for weeks on end on the side that faces the Sun, and extremely cold on the opposite side. And so, and then the strong tidal forces basically forces the rotation axis tilt to go to 0, which means you're not going to have seasons. And in order for you to avoid, by the way, if you wait long enough, our planet Earth will be tidally locked to the Sun. Fortunately, that won't happen for another 40 billion years. On the other hand, because the tidal interaction goes up with a 4th power of the distance between the star and its planet, just push our planet Earth 1% closer than it is to our star, then we would experience tidal interactions that would rule out the possibility of advanced life, which is the basis for the final statement. The star mass must equal the sun's mass to within 1% precision in order to avoid a problem with tidal locking. And then there's the astrosphere, a habitable zone. And this is referring to the atmosphere of the star. Our star, the Sun, has an atmosphere, and it actually blows out a wind, the solar wind. And that solar wind is a good thing for us in that that solar wind pushes away the deadly cosmic radiation. But if you get too strong of a stellar wind, the stellar wind proves deadly for life. But if it's not strong enough, the cosmic radiation is deadly for life. We happen to be orbiting our star where the radiation from the sun, the wind, balances out the radiation we get from the rest of the universe and actually creates a safe spot for us to be able to exist. On the other hand, none of that would work unless we had a strong magnetic field that shields us from both the solar radiation and the cosmic radiation. And then we have the atmospheric electric field. And what we discovered is that planets with an atmosphere, the closer they are to the host star, the stronger the electric field they have in their atmosphere. And so, for example, just last year, we measured the electric field in the atmosphere of Venus, Earth, and Mars. And we discovered is because Venus is a little bit closer to our star, the sun, it has an atmospheric electric field of about 10 volts. For the Earth and Mars, it's less than 2 volts. Now, when it gets up as high as 10 volts, it basically desiccates the planet. And so it explains why, even though Venus has got such a thick atmosphere and potentially could have water on it, because of its electric field, it has become bone dry. And then the one that was discovered a year ago was what's called the Milankovitch cycles. And this is referring to the fact that the temperature, for example, planet Earth varies over time scales of about 100,000 years. And that variation is because of the change in the tilt of our rotation axis. And you say, what causes that rotation axis to tilt back and forth? It's basically the tidal interaction of the moon and the sun, but the tilt isn't very much. It's only about 2 degrees. So we go from, say, 22 degrees to 24 degrees over a time scale of 41,000 years. Now, this is not true of the other planets. The other planets, their rotation axis tilt goes back and forth by 60 to 90 degrees. And if that were to happen, there'd be no possibility for animal life on the planet. The seasonal changes would just be too drastic. What prevents our rotation axis tilt from varying by not more than 2 degrees is our moon. We have a gigantic moon orbiting a small planet. And it's because of that single gigantic moon orbiting our relatively small planet that our rotation axis is stable. And this is where the moon is unique. If you look at the mass of our moon compared to the mass of its host planet, it's 50 times bigger than any other known moon. And so we're literally living on the only planet-moon system where the rotation axis tilt is only plus or minus 2 degrees. Nevertheless, that variation of 2 degrees is one of the big factors explaining why we have an ice age cycle, why we live on a planet where the coverage of ice varies from 10% to about 23% over a time scale of 40 to 100,000 years. The other thing that changes the temperature of the surface of the planet is a very tiny variation in the shape of our orbit, the eccentricity of our orbit. And so when the orbit of planet Earth becomes more elliptical, we get warmer. When it's less elliptical, we become colder. And that's the secondary effect driving our ice age cycle. So for example, this is currently what the ice age cycle looks like, where you got about a 90,000 year period where you got 20 to 23% of the planet covered with ice, and then you have what's called an interglacial, where it drops down to about 10%. And right now, we're in an interglacial. And for the last 800,000 years, it's been 90,000 years of lots of ice, with 10,000 years of a smaller amount of ice. Now, what we've seen on extrasolar planets is that typically you will get a very large Milankovitch cycle. So for example, this is the rotation axis tilt variation of Mars. where it tilts back and forth by 60 degrees, explains why, for example, in spite of Mars being bombarded with water-rich comets, comets are about 85% frozen water. And Mars collects these on a daily basis, so does Earth for that matter. But we notice on Mars, the ice caps are relatively small. The reason why they're small is because of the change in the rotation axis tilt. That when the rotation axis changes over, that exposes the ice cap to warmer radiation from the sun, which causes the ice cap to disappear, and it takes new comets to form another one. And likewise, we notice that in most planetary systems, you get a rather big change in the shape of the orbit. The bottom line is one of two things happens to the planets that are the most Earth-like, is they wind up either becoming completely bone dry or totally covered with ice. And so this is another fine-tuned feature we see on our planet Earth, is that we do get an ice age cycle, but we get a subtle ice age cycle rather than an ice age cycle that causes us to become completely bone dry or totally covered with ice. Now, for the rest of the talk, I'm going to focus on what we need here on planet Earth in order for billions of us humans to exist here at one time. Now, you don't need an ice age cycle if all you want is a few hundred humans wandering around in a small region. But if you want billions of us here, it's crucial we be living during an ice age cycle, and I'll explain why. It's also important we be living at a time when our sun is middle-aged. It has to be almost exactly middle-aged for us to be able to be here. And number three, we have to be living in an ice age cycle where we're in an episode of extreme climate stability. You've probably heard a lot about global warming and climate change. What you may not have heard of is that the past 9,500 years have been the most extreme period of climate stability our planet has ever observed. And so the stability we've been enjoying for the past 9,500 years is not the norm. It's the exception. It's the extreme exception. The norm is climate instability. Now, if we look at what we see here in our North America, of all the continents, experiences the most extreme effects of the ice age cycle. For the whole planet, the ice varies from about 10% coverage to about 20 to 23% coverage. And that is true of North America. When you're at the minimum, 10% of our continent is covered with ice. But notice most of it is on Greenland. Okay, at the height of the last ice age, this was 26,000 years ago, 55% of our planet was covered with ice. In fact, all the way down here to Southern California, we had thousands of feet of ice covering it. That's where Yosemite Valley was formed. It was formed by the retreating of ice left over from the last ice age. And this is what it looks like right now. And this is what the ice age cycle looks like. But what you'll see in my book, Improbable Planet, are a dozen reasons why to have billions of humans living on the planet at one time, in order to have any kind of civilization beyond a Stone Age technology, it's critical that we be living during an ice age cycle. And I'm going to give you just a few of the reasons why. Number one is we need melting water. Liquid water melting from glaciers left over from the last ice age in order to water the great agricultural plains. I mean, if you look at a globe, in fact, let me just show you this one. This kind of shows you the northern hemisphere and what it looked like during the last ice age. And the turquoise color you see there, the blue color, basically shows those regions of the northern hemisphere that were covered with a minimum thickness of 1,000 feet of ice. And then that ice began to melt, and it's the melting of that ice that feeds the great rivers that water the great agricultural plains. And what you see here is a Tibetan ice field. It's now only covering about 1 million square miles, but it's the melting of ice left over from the last ice age that feeds all the great rivers of China, India, and Southeast Asia. And so we're able to feed 3 billion people in Southeast Asia thanks to ice that's been left over from the last ice age. And when all that ice melts away, we're no longer going to be able to sustain billions of people on the face of the earth. The same thing is true of North America. We still have ice left over from the last ice age that covers the Cordilleran Mountains, the Rocky Mountains, and several other mountain ranges in the west of the U.S., and that feeds the Missouri, the Mississippi, it feeds the Fraser, the Columbia, the North and South Saskatchewan rivers, and it's these rivers fed by the melting of ice left over from the last ice age that explains why we here in North America can grow as much food as we grow and why we can export it to all the nations of the world. And likewise, you can look at Europe. It's ice in the Alps, it's ice in the Caucasus that's feeding the rivers that allow Europe and Western Asia to grow all the food that they're able to grow. Incidentally, the same thing's true of the southern hemisphere. Ice left over from the last ice age in Patagonia is basically explains why you can grow as much food as we grow in South America, and this is even true of the Amazon. There's still ice left over from the last ice age in the high mountains in the Andes that's feeding the Amazon and other rivers that make possible. The other thing we notice is that the ice age cycle produces fertilization events. That when ice begins to recede off the high plateaus that were covered with thousands of feet of ice, the recession of that ice, and the ice recedes very quickly. Literally in 1,000 years, you have thousands of feet of ice dropping down to just a few inches or a few feet. And it's that rapid deglaciation that sets up powerful winds that blow dust off the high plateaus and dumps that dust on the low agricultural plains. And that dust is nutrient rich. So with each ice age cycle, we get a fertilization event. And so, for example, the reason why we're able to grow so much food in India and China is because they've gotten a huge load of nutrient-rich dust coming off the high plateaus of Central Asia. And that's also happened in Europe and in North America. The other thing that happens is that when you got all that ice forced down on the continental land masses and it melts, you get a rebound effect. And that rebound, that gravitational rebound, ignites volcanoes all over the world. So, for example, a paper was published just 6 months ago making the point that with the receding of ice left over from the last ice age, roughly 15,000 years ago, where you get this rapid recession of ice, it ignited volcanoes all over the world. And when volcanoes ignite, they dump nutrient-rich dust and ash all over the world. And so by two separate means, we get the fertilization of these great agricultural plains. And again, without that, we wouldn't be able to produce the food quantity that we produce. But you know, I like mountaineering and hiking. That's my hobby. And I go to places just to see these beautiful canyons and waterfalls and mountains and cirques. That was all carved during the last ice age. And if you actually look at the past 4.5 billion year history of the Earth, the last ice age in the ice age cycle was the most severe ice age in the ice age cycle. It was also the one that had the most rapid movement back and forth of ice. It wasn't just the buildup of ice and recession of ice. There was actually several buildups of ice, recession, buildup, but very rapid movement of that ice. And what that has created is the most spectacular scenery our planet Earth has ever had. We are living in the most beautiful time in the history of our planet Earth. We're living at the most scenic moment. So, for example, a couple of summers ago, I took my family and several friends into this particular canyon. It's in British Columbia, where the walls are 2,000 vertical granite feet. There's glaciers all around. And when I was in the middle of this canyon, I could count 25 large waterfalls flowing off the canyon walls into the canyon floor. And with all that water flowing in, the canyon floor was filled with wild strawberries, raspberries, blueberries, loaded with wonderful life forms that we could commune with. This is unique to our time. At no other time in the history of Earth have we had that, and I think the Creator knew in advance there would come a time when most of us would live in cities, and most of us would spend our workday behind a computer screen. And in order to maintain our sanity, we'd need to be able to get to places like this once in a while. That's how I keep my sanity. I make sure I get to one of these places every once in a while. And hey, California is a place where we've had some beautiful canyons and scenery carved, thanks to the last ice age. Okay. But if you read the book, I give you another 8 reasons why we have to be living in an ice age cycle in order to be able to have, one example I'll give you is we live at a time, thanks to the ice age cycle we're in, where we've got abundant hydropower capability. With the receding of the ice, there's all these lakes, rivers, canyons, and cirques that are created. At no other time in the history of our planet Earth have we had the water power resources that we have today. I grew up in Canada. Canada's a place where they get all of their electricity from water power. All of Canada was covered with ice in the last ice age. In fact, they produced so much water power they exported to the US. Okay. The second reason I mentioned, though, was we have to be living at a time when the sun is perfectly middle-aged. And stars are a lot like human beings. They're unstable when they're young, they're unstable when they're old. They're maximally stable when they're middle-aged. Now, in the case of human beings, the stability period is more than half of your lifetime. In the case of stars, that's not the case. The stability time is extremely brief relative to their entire burning period. Now, of all stars, our star, the sun, has the least flaring activity. But it still flares a lot. And when it's young, it's flaring, and when it's old, it's flaring. Now, this vertical scale here is logarithmic. And so when the sun was young, the frequency and intensity of its flares was 1,000,000 times greater than it is today. And explains why, for example, for the first 3 billion years of the history of life on planet Earth, all you've got are microbes. Because the flaring activity was so intense from the sun, it would only permit the existence of microbial life. So if you want to know why such a long period goes by before you see plants and animals, well, the sun is one reason. It simply doesn't permit anything more advanced than microbial life to exist. And as we go into the future, the flaring activity will pick up again. But what I want you to notice, this is where we are right now. We are living at the time when the solar flaring activity is minimal. So if we were here any earlier or any later, the flaring activity would be too great. Matter of fact, there was a solar flare in 1859. And if we were to get a flare like that today, it would knock out our GPS satellites, it would knock out your phone communication, and the words of my 2 sons, it would be the end of civilization as we know it. Okay. And we haven't had a flare like that since 150 years ago. The flaring minimum occurs when the sun is 4.57 billion years old. That's how old the sun is right now. However, what we've been able to determine by looking at both the photons coming out of the core of the sun and the neutrinos coming out of the core of the sun is that the sun entered an extremely stable luminosity phase beginning a little less than 50,000 years ago. And those same measurements tell us we'll exit that phase a little less than 50,000 years into the future. In other words, there's a time window briefer than 100,000 years where you get the necessary luminosity stability from the sun to make possible this period of climate stability we're enjoying right now. We're right in the middle of that narrow window. So the sun can burn hydrogen for 9 billion years, but only for about 90,000 years do you get the kind of luminosity stability that makes possible the existence of human civilization. And of course, you have to be in an interglacial, which makes the period about 10,000 years wide. Now, this poses a major problem, however. The sun, as it continues to fuse hydrogen into helium, gets brighter and brighter as it continues. So this is what the luminosity of the sun looks like over the history of life. Now, the luminosity goes up when the sun is young because it's accumulating mass. The luminosity of a star goes up with the fourth power of its mass. It stops accumulating mass, and then it loses about 6% of its mass. And that explains this luminosity drop you see here. But then it stops losing mass, and it ignites nuclear fusion in the nuclear core of the sun. And this starts the process of fusing hydrogen into helium. Our sun is basically a gigantic hydrogen bomb. And so that begins to cause the luminosity to increase. It increases, why? Because as hydrogen is fused into helium, that increases the density in the core of our sun. And that increasing density means that the sun burns ever more efficiently. And so it explains why the sun has brightened by more than 20% over the history of life on planet Earth. Now, throughout this period of the history of life on planet Earth, for 90% of that history, our planet has had no ice at all. And today we have ice. So that's the big paradox. Why do we have ice on planet Earth today when the sun is brighter than it's ever been in the history of life? This should be a time when we got no ice whatsoever, and yet we've got ice. And so how do we explain that? Well, just recently, geophysicists and astronomers have come up with an explanation for why, in spite of the sun being brighter than it's ever been in the history of life, we have this cycle of ice between 10 and 23%. And what they discovered is a combination of astronomical events and geophysical events. I'll give you the geophysical events first. There have been 5 unprecedented plate tectonic events that explain how the planet got cold enough where we have ice. So we began to get ice about 3 million years ago. Before that, we had no ice at all. In fact, for the past 500 million years, there's been no ice. But today we got ice. Okay, one reason is what happened to Antarctica. Antarctica was attached to Australia. It broke off from Australia, but remained attached to South America. And beginning about 11, 15 million years ago, it broke off from South America and began to move rapidly towards the South Pole. And so there's this rapid tectonic movement away from South America towards the South Pole, and when it got over the South Pole, it stopped moving. Right when it got over the South Pole. And so here we are, Antarctica, the South Pole, no longer is it moving. It's stable there, but Antarctica ranks as the most isolated continent on planet Earth today. What you notice is there's open ocean water all around Antarctica. And because of that open ocean water, you get powerful ocean currents and winds. Now, if you're like me, when I was in elementary school, our teachers had us read these novels of the sailing ship era. And those novels talk about the roaring 40s and the roaring 50s. And that's a reference to the powerful winds and currents that rip around Antarctica. And it's because of those winds and currents, literally moving at about 40 miles an hour, that we wind up with Antarctica being cooled. So it's not just the fact that it's right over the South Pole. That alone would not explain why you get ice on Antarctica. It took a combination of it being right over the South Pole, plus these powerful currents and winds that cooled Antarctica enough where ice began to accumulate. And so that's where ice began to appear on planet Earth for the first time, was over Antarctica. But there's another cooling effect. this current that was going around Antarctica, once we get ice covering most of Antarctica, that begins to cool the rest of the planet. Why? Because ice reflects sunlight with about 60% efficiency, whereas ground and rock reflects it with about 10 to 15% efficiency. And so with all that ice covering Antarctica, that had a cooling effect on the planet. And then what happened was this circulation began to push a current up through the Atlantic Ocean. So cold water from Antarctica began to move up the Atlantic Ocean and began to cool all the continental land masses that are adjacent to the Atlantic Ocean. Okay, that's tectonic event number one. Tectonic event number two is what happened to Greenland. Greenland, if you go back 50 million years ago, was situated just off of Newfoundland here. Moreover, it was low elevation, and so it had no ice. But then it got a tectonic kick and began to move rapidly up towards Baffin Island and towards the North Pole. And as it moved northward by 1,100 miles, it moved over a hot plume. Now, Hawaii is an example of a current hot plume, where the Hawaiian Islands are sitting over a region where you got this upwelling deep mantle material from the interior of the earth coming up towards the surface, breaking through the crust and forming the Hawaiian Islands. Hawaii is the fastest growing state in the Union because of that hot plume effect. Well, that also happened when Greenland moved over its current location. It got situated over a hot plume, and what that did is it pushed the land mass of Greenland from being less than 500 feet above sea level to where it's now 7,000 to 8,000 feet above sea level. And it's a combination of it being pushed towards the North Pole and its land mass going up by 7,000 or 8,000 feet that caused ice to form over Greenland. You need both, its location plus the pushing up of its land elevation. Event number three is what happened to Pangaea. Planet Earth has a supercontinent cycle where the continents come together and make one continent, break apart, and come together and break apart. It happens about every 500 million years. And Pangaea was 250 million years ago where we just had the one continent that broke apart. But this is the first time in the supercontinent cycle where most of the landmass went into the northern hemisphere and moved into the northern hemisphere in such a way that the Arctic Ocean got almost completely enclosed by land masses. And land masses are always warmer than open ocean water. And it was the enclosure of the Arctic Sea. And so we see here is a Greenland moved north and it plugged the gap. And so we have islands and land masses encompassing the Arctic Ocean, and what that did is it caused a cap to form, an ice cap to form. Now, open ocean water reflects sunlight with 6% efficiency only. Ice reflects sunlight with 60% efficiency. And so with the forming of this cap of ice over the Arctic Ocean, it had a cooling effect on the whole planet. And so first we get ice over Greenland, then or ice over Antarctica, then ice over Greenland, then ice over the Arctic Ocean. And with all that high reflectivity of sunlight, it has a cooling effect on the entire planet. Event number 4 is what happened to North and South America. North and South America, if you go back 10 million years, were separated continents. And what that allowed was for warm Pacific Ocean water to come into the Atlantic. Now remember what I said before, we got this movement of cold water from Antarctica going up through the Atlantic. But the cooling effect was blunted by this warm equatorial water from the Pacific coming between North and South America. But that got blocked with the formation of the Isthmus of Panama. That formed a land barrier that prevented warm Pacific Ocean water from going into the equatorial Atlantic. And that dramatically increased the cooling effect of that cold water coming up from Antarctica, and dramatically increased the cooling effect of the land masses adjoining the Atlantic. Event number 5 was the most important and the dramatic of them all. And this is what happened to the Indian subcontinent. 70 million years ago, the Indian subcontinent was attached to the island of Madagascar. It broke off from Madagascar and then rushed towards the towards Asia. And it moved at a rate of 22 centimeters per year. That's an all-time world record for tectonic plate movement. Okay, now a really rapid tectonic plate movement is 2 centimeters per year. And so this is literally 11 times faster than what's considered to be a really rapid movement. To give you a visual demonstration, a typical rapid tectonic plate movement scaled down would be like me walking like this. Okay, then we're going to show you what 22 centimeters per year would look like. It'd be like me running across the stage. And so what happened is that when India crashed into Asia, it was a huge impact event. And so we have, starting 10 million years ago, the Indian subcontinent rushing towards Asia at this high speed of 22 centimeters per year, and it caused the ocean floor between Asia and the Indian subcontinent to crumple up. And those are the Himalayas. The Himalayan mountains are pushed up seafloor. It explains why when you climb Mount Everest, you'll find seashells near the top of Mount Everest, because Mount Everest is crumpled up seafloor. Now, because of how rapidly the Indian subcontinent smashed into Asia, those Himalayan mountains have been pushed up to nearly 30,000 feet elevation. And again, the higher the elevation, the colder it gets. And so what you have are the Himalayan mountains covered with all these glaciers and ice. And what's interesting here is now you've got glaciers and ice not at 70 degrees north or south latitude. You got it near the equator. And when sunlight reflects off of ice near the equator, it has 4 times the cooling effect of ice, of sunlight that reflects off of high latitude parts of the world. So of these 5 events, the one that has the most dramatic effect is what's happened to India. It's basically recreated an equatorial ice cap. Because as India collided into Asia, it not only formed the Himalayas, it pushed up Tibet. The Tibetan Plateau has been pushed up to an average elevation of 17,000 feet. And so ice not only covers the Himalayas, it covers the Tibetan Plateau, an area that covers about 1 million square miles. And incidentally, if you were to ask me, what's the second fastest tectonic plate movement ever observed in the entire history of the Earth? It's the current movement of India into Asia. The collision is not yet finished. India is moving into Asia at a rate of 5 centimeters per year. So it explains why the Himalayas get taller every year. You know, we say Sir Edmund Hillary was the first man to climb the world's tallest mountain. Well, not really, because Mount Everest today is almost 2 feet higher than it was when Sir Edmund Hillary climbed it, thanks to the current movement of Asia India into Asia. It also explains why every ice age in the ice age cycle has gotten a little bit more severe than the previous one. Why? Because the Tibetan Plateau is continuing to go up. And as it goes up, more and more ice covers the Tibetan Plateau during East Ice Age. Basically explains why we're still able to grow a huge amount of food in India and Asia and Southeast Asia during this interglacial, because the last glacial was so severe, we still have some ice. I mean, it's been 13,000 years since the end of the last ice age cycle. That ice should have all gone away, but because of how severe the last ice age is, we still got ice. And so there's still melting water from that ice that's able to feed the great rivers. Now, 3 years ago, geophysicists felt this was adequate to explain the Ice Age cycle. Astronomers jumped in and said, no, wait a minute. Even with these 5 unprecedented, amazing tectonic events all happening simultaneously, and by the way, it's critical, they all have to happen at the same time. Otherwise, you don't get the combination that gives you adequate cooling. But when astronomers looked at this and they added it all up, they said it's still not enough to explain why we got ice in light of how bright the sun is. It says there must be an additional cooling effect that we've overlooked to explain why we have this ice. This has all been published in the past 2 years. Number one, they figured out, okay, what actually started this ice accumulating over Antarctica? And they determined that a collision event 2.58 million years ago, just south of Chile. This is newly discovered. That little red dot that you see at the bottom there, that represents a place where an asteroid hit the Earth 2.58 million years ago. And it hit in a place where the ocean depth was about 17,000 feet. And so it explains why we didn't discover the crater. Matter of fact, what happened is when they sent an exploration ship there and did deep sea core drills, they did not find a crater. Because it hit in such deep water, there is no crater at the bottom. But what they found is over a region of 60,000 square miles, they found the isotope signature that tells them there had to be a major asteroid that hit that area. And only recently have they done enough core drills to determine just how big that asteroid had to be. Bottom line, it had to be at least 1 kilometer in diameter, and it could be as much as 2 kilometers in diameter. That means it's one of the biggest asteroids to strike the Earth in the past billion years. When it hit the ocean, it caused gigantic tsunamis 1,000 feet high to radiate throughout the Pacific Ocean. Matter of fact, they've been able to confirm that this indeed was a giant asteroid collision event by looking at the tsunami wash-up effects that they found in Australia, New Zealand, China. They found it in North and South America, literally all over the Pacific Ocean. We see this wash of debris that came up against the coastal land regions, and they all date to 2.58 million years ago. And the degree of wash-up says, yes, we really are looking at tidal waves 1,000 feet high. Now, because of how big that asteroid was, it caused seawater to be thrown up into the atmosphere, evaporated. It did hit the bottom. It didn't make a crater, but it caused all the material at the bottom of the ocean floor likewise to be pushed up into the atmosphere, including all the minerals that were in the salt water of the ocean. It basically formed an aerosol cloud over the Earth that blocked out the light of the sun for several years and caused a cloud that actually reflected away sunlight, and astronomers have been able to determine this was the most critical factor in cooling the planet in order to have developed that Ice Age cycle. And incidentally, the date for the ignition of the Ice Age cycle, 2.58 million years ago. The same date we get for the asteroid collision. So that's what started the Ice Age cycle. But it took the combination of this asteroid collision event plus the 5 simultaneous tectonic events to explain why we're in an ice age right now. Now, 2.58 million years ago, the Ice Age cycle got ignited, but it was a 41,000-year cycle, basically driven by the variation in the tilt of our rotation axis. It goes back and forth with a cycle of 41,000 years. Today, we have a 100,000-year cycle. That's a good thing. If you've got a 41,000-year cycle, the warm interglacials only last 2,000 or 3,000 years. That's not enough time for humans to launch global civilization. We need a minimum of 10,000 years. Well, newly discovered was another asteroid collision event. This one in the South China Sea. This one dated to 800,000 years ago. And there was several large islands here. When this asteroid hit, it basically obliterated those islands, so all we have today are a few scattered tiny islands called the Spratly Islands. You're probably aware that there's 6 nations all competing with one another for sovereignty over these islands: China, the Philippines, Vietnam. Lots of nations are all claiming sovereignty over those islands because of their military importance, but they're tiny islands, basically obliterated by this event. But this event sent up a huge debris cloud that's now circulating throughout our solar system, and we pass through it every 100,000 years, and explains why the Ice Age cycle changed from a 41,000-year period to a 100,000-year period. And so it explains why, too, we see it being predominantly dominated by the change in our eccentricity as opposed to our rotation axis tilt. Now, we've been able to drill ice cores in the Alps, in Greenland, and Antarctica that basically tell us the global mean temperature throughout the Ice Age cycle. This is the most detailed of them from Antarctica, and it basically shows you the previous 4 ice ages. And what you can see is how the temperature goes up rapidly, and where you go down to just 10% ice coverage, and then you get this long period where you've got 20% plus. But what I want you to notice is how the temperature jumps up and down. And so, for example, this is the previous ice age, where you get rather dramatic movements of the global mean temperature. It explains why the ice sheets were going back and forth at such a rapid rate. Incidentally, it also explains why humans that were living here 30, 40,000 years ago were not able to develop global civilization. We now have evidence that humans living 35,000 years ago actually were developing bakery industry. They were planting grains of different kinds, harvesting those grains, grinding the grains, roasting the grains, and making bakery products, but all on a very small scale. And let me just show you, for example, what they're up against. This is a detailed picture of the global mean temperature during the last ice age, where you see that the temperature is jumping up and down by 18 degrees Fahrenheit over time scales of just a few centuries. With the temperature jumping up and down by that much, with that degree of climate instability, it's impossible for humans, regardless of intellect and endeavor, to develop any kind of sophisticated civilization. In fact, what was happening at that time, humans would be planting crops, but they would plant maybe 12 to 15 different kinds of crops, knowing that the climate instability would destroy, say, 10 of them, and they feed their families on the ones that actually survived. It forced humans to have small farms where it was mixed farming. Same thing with their animals. They were domesticating animals, but all on a small scale because they didn't know which kind of animal would survive the climate instability. Until we enter 9,500 years ago. And what you see there is, for the first time in the history of the Ice Age cycle, everything becomes stable. In fact, it's more stable than what that graph indicates. This actually shows you the temperature as we're coming out of the last ice age, going up and down, and then we have this period of the past 9,500 years where the global mean temperature is extremely stable. So extremely stable that for the first time, humans can begin to specialize. This is when we see humans having farms that are like several square miles, where they only grow wheat, or they only grow rice, or they only grow corn, because they could count on the fact that they would get an abundant harvest that they could trade for products with other individuals. Also the first time we see people specializing in goats or sheep, where people would have, say, 10,000 sheep, and that would be their whole industry. And it's a time when you actually have villages where they're not growing food at all. They're making pottery products or engaged in metallurgy and trading with one another. This was the launch of human civilization. where you got villages, transportation systems, people specializing, where during the last ice age, this period here, 98% plus of the human workforce was devoted to coming up with enough food to feed everybody. What is it like today in the United States? 1% of our workforce, less than 1% of our workforce feeds the rest of us, which means 99% of us do not have to be involved in agricultural industry. We can be doing things like engineering, science, art, music, computer coding, technological development. It explains why technology today is advancing as rapidly as it is, because we got the climate stability where you can actually have most of our workforce devoted to other enterprises besides coming up with enough food. Now, typically what happens is as you come out of an ice age, the temperature goes up so extremely fast, you wind up dropping into an ice age. Global warming always brings on global cooling. We now know why. When the temperature goes up about 2 degrees centigrade past where we are right now, it melts the polar ice cap. When you melt the polar ice cap, instead of 60% of the sunlight being reflected away, we have only 6% reflected away, which means the ocean in the Arctic Sea basically absorbs solar heat, and what happens to that solar heat? It makes water vapor that now falls on Siberia and Canada as snow. The only reason why Canada is not covered with thousands of feet of ice today, it's a desert. It only gets less than 10 inches of precipitation per year, not enough for the ice to accumulate. But if you melt the polar ice cap, which is what will happen with ongoing global warming, then you get 20 inches of precipitation falling over Canada, which is enough to cover all of Canada with thousands of feet of ice in short order, and likewise that happens in Siberia. What prevented that from happening this time is you got this major cooling event, the Younger Dryas event. The temperature is going up, then it drops down, and it stays down and doesn't reach its maximum. Just a few months ago, we came up with the answer. What explains this interruption in the typical warming you get with the ice age cycle, where we got this dramatic cooling event, such a dramatic cooling event, it stopped the temperature from going up to its normal maximum and stopped the melting of the polar ice cap. Well, just a few months ago, they found another place in the world where there was an asteroid collision. Now, the one off of Chile, it was difficult to find because it was under 17,000 feet of ocean water. This next one was difficult to find because it's under 3,000 feet of ice. That little red dot there shows you where it hit in Greenland. And the crater is literally 3,000 feet below the surface ice. What we now understand is that when that hit, it melted a lot of the ice in Greenland, but it took place at a place where it also hit some landmass, and it caused debris to fall all over North America. Now, at that time, when the asteroid hit, we're talking just 12,000 years ago, when it hit, we have ice rapidly receding from North America, but it formed a gigantic glacial lake. This is Lake Agassiz, this huge lake over Minnesota and Manitoba and Saskatchewan. So this is cold glacial water. And when the asteroid hit on Greenland, it caused a bombardment of boulders to fall in this region. And what was happening was Lake Agassiz was draining down towards the Gulf of Mexico. The bombardment blocked that flow and forced the water from Lake Agassiz to go out through the St. Lawrence, and the rest of it to go up through the Mackenzie into the Arctic. But in both cases, that cold glacial water, fresh water, began to surround Greenland and basically pushed back the Gulf Stream and resulted in a major global cooling effect. And explains why we've not yet melted the polar ice cap, and explains why we've had this period of extreme climate stability. And is this a coincidence? It's also that time when we have no nearby supernova eruptions. My peers have actually determined recent supernova events. So for example, during the last ice age, from 50,000 years ago, actually 40,000 years ago, to 15,000 years ago, there were 4 supernova eruptions that happened closer to us than 800 light years, some as close as 300 light years. Not enough to kill us, but enough to impact our health, and enough to significantly degrade agricultural productivity. And so that also explains why humans during the last ice age were not able to grow enough food to set free people to do engineering and science. The supernova were getting in the way. And incidentally, that was the typical rate. That's the typical rate for a Milky Way galaxy. During this period of extreme climate stability that we've had for the past 9,500 years is identical to the period where we've had no nearby supernova eruptions. This is a list of all the supernovae that have happened in the past 10,000 years. Notice the closest is 5,000 light years away. Far enough away where it has zero effect on human health and zero effect on the productivity of our cultivated fields. But this is the only period in the history of the Earth where we haven't had any supernova closer to us than 5,000 light years. In fact, it's the only period where we've had none closer than 1,000 light years. And this is something I explain in my book, Improbable Planet, is that we're living in multiple narrow time windows that all exactly overlap to give us a period of extreme climate stability. The other thing that I think is really interesting is that this asteroid that hit in Greenland prevented the temperature from going up, but there's also a period when our rotation axis tilt is declining, which means we're getting colder and colder. As a matter of fact, let me see if I can pull this. Well, no, it'll take too much time. But you'll see in a blog article that I've written how the global mean temperature over the past 9,500 years is declined by 0.9 degrees centigrade. It should have declined by 15 degrees centigrade. It didn't happen. What prevented that from happening is as the rotation axis tilt was cooling the planet, humans took advantage of the climate stability and began to domesticate cows and domesticate rice and cut down forests and make pasture lands for their cows. All those are warming effects. Cows emit huge quantities of methane and carbon dioxide, and that actually warms the planet. When we irrigate the fields to make rice, that produces methane. The methane in the atmosphere has doubled since humans began to launch global civilization. And methane is a very powerful greenhouse gas. And so as we have the rotation axis tilt wanting to cool the planet by 12 degrees centigrade, we got human activity through the domestication of rice, the cutting down of trees, and the domestication of cows, warming the planet by virtually the identical amount. Now, it's such that the human activity didn't quite balance the cooling effect. And so over 9,500 years, the temperature has dropped by 0.8 degrees, but only by 0.8 degrees. But what I can share with you, in the last 70 years, human activity has accelerated the warming of the planet, where in the last 70 years, the global mean temperature has gone up 1 degree centigrade. If it goes up another 1.5 degrees, we will melt the polar ice cap and bring on an ice age. But as it is, we've had 9,500 years of extreme climate stability. And it's that extreme climate stability that's made possible the existence of global human civilization, the setting free of enough people where we can have billions of us living here at one time, where billions of us are not engaged in agricultural activity, where billions of us are engaged in engineering, science, mathematics, medicine, art, music, and explains why we have such a rich culture today. Now, you heard earlier I'm not only an astrophysicist, I'm also a pastor of a church that's sandwiched between Caltech and the Jet Propulsion Laboratory. We're also really close to the headquarters of the Skeptic Society and to Fuller Seminary. I lead a class for skeptics every Sunday. And it's a class where we basically say, hey, I got a curriculum I'm teaching, but you can interrupt me anytime with questions on any topics. And because we always have so many of these atheists and skeptics from the Skeptic Society coming in, and all these engineers and scientists from Caltech and the Jet Propulsion Laboratory, every Sunday is an engaging debate. But it's an engaging debate where we deal with issues like you heard today. And basically have people think about this. Is this some kind of cosmic accident? And basically I'm telling you here today, none of this is an accident. Every event in the universe, every event in the history of the earth, every event in the history of life over the past 3.8 billion years, and every component of the universe, Earth and Earth's life, plays a role in making it possible for billions of us to live in this planet at one time, and to develop the technology and the education and the capacity to investigate the universe, where we realize the universe is not only fine-tuned to make possible our existence, it's fine-tuned to bring about the complete eradication of evil and suffering. Something I've written about in my book, Why the Universe is the Way It Is. The whole universe has to exist to make it possible for one planet on which humans can live. The whole universe. Make it any bigger, any smaller, we wouldn't be here. But the laws of physics, the size of the universe, the mass of the universe, and even the space-time dimensions are all designed to be tools in the hand of the Creator to completely eradicate evil and suffering. And you heard in the introduction, I was not raised in a Christian home. I was raised by people who didn't believe. In fact, I didn't actually get to meet Christians until I showed up at Caltech to take up a research post as a research fellow. That's where I first met believers. However, by looking at the world's holy books, I noticed a difference. In Hinduism, Buddhism, Islam, Baha'i, and all the other religions, it's a one creation model. In Christianity, it's a two creation model. How God designs the universe with the laws of physics and the dimensions so that evil can be completely eradicated while human free will is being enhanced. And once that happens, once billions of people have had that experience, then God will take us from this creation into a brand new creation where evil will never exist again, where there'll be no suffering, where we'll no longer be constrained by gravity, thermodynamics, and electromagnetism, or be constrained to only 4 space-time dimensions. We'll be delivered into a realm where we'll be able to express our free will to far greater capacity than we can today. Before me was a great multitude that no one can count from every nation, tribe, people, and language, referring to the huge host of billions of people that'll be enjoying life in the new creation. And it's a place with radically different physics. And you can read about it in Improbable Planet and also my book, Why the Universe is the Way It Is. I'm going to devote the rest of the time to questions on any subject you care to raise. It doesn't have to be in what we talked about today. But I'm sure I've given you enough content that you could do that.
Thank you very much, Dr. Ross. We have some microphones coming around in just a second. I'm sure there's a lot of questions. That was a lot of information, a lot of interesting information, wasn't it? Wow, are you glad you came today? All right, just a second. We got some, yeah, exactly. Just a second, we got some mics coming around. Please wait till you get a mic. Anybody raise your hand if you've got a question? Yeah, there's one over here, one over there. Yeah, go ahead.
Yes.
It's on. It's on.
You talked about the asteroids hitting and impacting the climate. What's the chances of that happening again in the future to distort this timeline and climate?
Well, when these asteroid collision events were being discovered, there was a huge amount of skepticism amongst scientists. The skepticism arose because they said this is way too frequent of these kinds of events. Asteroids a kilometer across in diameter hit the Earth about once every 10 or 20 million years. And to get 3 of them in this short period of time, they just said this can't possibly be. However, we now have the evidence that makes this undeniable. We see the crater under that 3,000 feet of ice. We can see what happened at the Spratly Islands. We've done surveys at the bottom of the ocean floor off of Chile. There's no doubt that these events happened. There's no doubt that these are really big asteroids. But the question is, why so many big ones in such a tiny period of time? And why now? Because we're halfway between spiral arms. When you cross a spiral arm is when you really get an enhanced bombardment of asteroids and comets. And so a half billion years ago, we were being bombarded a lot more intensely. But this is a time when we should be getting very few collision events. And yet we got 3 really big ones in the recent history of the Earth. One as recent as just 12,000 years ago. And so the question is why, but as I write about in my book and my articles, notice that all 3 have to be exactly the size they are, hitting exactly the locations they are, at just the right time that they do, in order for us to have this a period of extreme climate stability. The Creator is throwing rocks at our planet, but he's actually hitting the target exactly where it needs to be and hitting it at just the right time with just the right intensity so we can actually enjoy a lecture in this theater hall today.
Mm-hmm. Right there.
Very interesting presentation. I just have one question, and that is, have you ever looked for what you would consider non-human life on other planets?
Yes, that's a question that was addressed about 40 years ago, where my colleagues were speculating maybe it's not life as we know it. And so they began to consider, what about the possibility of silicon-based life, or boron-based life, or arsenic-based life? And what they discovered is that carbon is the only game in town. Carbon is the only element in the periodic table where you have the necessary bonding stability and the bonding complexity to make all the proteins, DNA, and RNA, or the equivalent such molecules of sufficient complexity where life would be possible. And so it doesn't have to look like us, but it's got to be carbon-based. And when I write about the fine-tuning, and by the way, you can go to our website, reasons.org/fine-tuning. That will pop up for you a 300-page compendium where we list most of the fine-tuning evidence. And that fine-tuning evidence simply presupposes if it's life, it's got to be carbon-based. We don't care what kind of carbon-based life it is, but just simply the recognition it's carbon-based explains all the fine-tuning that you see in that compendium.
Got a question, please raise your hand. Yeah, and is there a mic back there? Raise your hand if you got a mic. Yeah, right there in the back.
Dr. Ross, can you explain to us about all the nuclear disasters we've had all over the world, how they're affecting our planet?
The nuclear disasters, things like Chernobyl, things like what happened in Japan
Correct.
a year ago. Fortunately, those have all been relatively minor nuclear disasters. Probably the most dramatic one was the Chernobyl one. And even today, it's not safe to walk around Chernobyl. However, I was in Kiev back in 1990, where people were worried about water from the Dnieper River. It was safe to drink, even though it went right by Chernobyl. So, but there are reasons why we should be careful with our nuclear reactors. And I mean, that's one reason why it's expensive as it is to build a nuclear reactor. But in favor of nuclear power, you actually release much more radiation, deadly radiation to the environment by burning coal than you do by getting electricity from nuclear fission. So nuclear fission is actually safer than burning coal. Coal's got uranium and thorium in it. When you burn it, it gets into the atmosphere, you breathe it. It's a good reason why we shouldn't be burning as much coal as we're burning.
Very interesting. Right down here.
I again would like to thank you for being here. This is very, very interesting. What do you make of the theory that during the formation of our solar system, that we were protected by another planet that kept asteroids and other particles away from us?
Yeah, that actually came out of Caltech in the 1980s. An astronomer I knew there actually found this infrared source. And there was a brief period of speculation that maybe what he discovered was a distant planet way beyond our solar system that played that protective role. We now know that infrared source is actually an extremely distant quasar. And we've done some searches around our solar system with much more advanced telescopes. And the bottom line is there is no planet Nibiru or planet X that's orbiting our solar system. However, we do know there might be a planet about 10 times the mass of the Earth that could be orbiting about 50 times farther away than Neptune orbits. In fact, there's what we discovered is several of the distant asteroid orbits in the Kuiper Belt overlap, and the overlap suggests, doesn't prove, but suggests there may be this distant small planet orbiting the solar system. And several astronomers are trying to determine whether or not that planet exists. It was actually predicted by a group of French astronomers, French and American astronomers, who noticed something. It was actually built into my talk, but I skipped it because of time. How we're now able to see asteroid and comet belts outside of our solar system. So, but what we're seeing is most of them, 90% of the stars that have planets have no asteroid and comet belts. The 10% that do have asteroid and comet belts that are 1,000 times bigger than ours. And if they're 1,000 times bigger, you're going to be bombarded all the time with giant asteroid things. Not a pleasant thing to think about. However, to have none poses a problem because we lose a little bit of water to outer space. That water is replaced by comets bringing water back in. Remember I was talking about how Mars gets its ice cap replaced? Well, likewise, our planet Earth, the water that we lose is replaced by comets bringing fresh supplies of water in. But if you got no comets, that's not going to happen, and that means our Earth would be desiccated over a long period of time. And what we now know is why we're unique. Most planetary systems have gas giant planets like Jupiter and Saturn. They migrate in towards their star, and typically they migrate all the way into the orbit of Earth and Venus. And when that happens, they obliterate all the comet and asteroid belts. And so most of the planetary systems we observe outside of our solar system, the gas giants are orbiting close to their stars, and explains why they have no asteroid and comet belts. Now, the ones that do have asteroid and comet belts are where the gas giants stay far away. Gas giant planets can only form far from their stars because you need that to get all that gas to be in a frozen state. And for those, they don't migrate at all. What was unique about our solar system, Jupiter, Saturn, Uranus, and Neptune migrated in towards our sun, and it reached a point where Jupiter was making exactly 2 orbits for every single orbit of Saturn, and because Jupiter and Saturn are the most massive of the gas giants and the closest to the star of the sun, it caused a reversal. And so the gas giants moved in, stopped, changed direction, and moved back out. That explains why we have small asteroid and comet belts, but they've not been completely obliterated. But to make that model work, you have to have 5 gas giant planets where one of the 5 gets kicked out. And the one that got kicked out may be this distant planet 50 times farther away than Neptune, or it may got completely kicked out. Within a year or two, we'll know which model is right.
Got all that? I'm just amazing. Whoa, okay. Right over here, I see a question.
Yeah, this is something I've been curious about ever since Man on the Moon, and then we got those little carts running around Mars. Do you think anybody or will ever get anything on the sun, or is it just too damn hot?
Yeah, we're not going to be visiting the sun. If you get very close to the sun, it basically vaporizes your spaceship and vaporizes the astronauts.
I think I'll stay home then.
Yeah, I mean, you can certainly get closer to the sun than you can get to Mercury, not with people. And by the way, there is a new piece of research done on mice, which basically demonstrates that once you get outside of Earth's magnetosphere, your digestive tract gets destroyed. Say, how quickly? Within 90 days, which means we're not sending people to Mars, we're not sending people to Mercury. We can send people to the moon, because that's close enough that we can get there and back before our digestive tracts get destroyed. And the magnetosphere sometimes also includes the moon. But yeah, we now recognize Mars is going to be done with machines. Humans aren't going to get there. Wow. Unless there's some human you want to send there.
Elon Musk will make it there, yeah. Right over here.
Could you explain how the scientists know where Earth's land masses were millions of years ago?
Yes. We can actually trace the movement of these continents, so we can actually measure the movements they are today and project back in time. The other thing we notice is that we can see, for example, that South America and Africa had to be joined together. If you actually look at the west coast from the east coast of South America and the west coast of Africa, you can see how they fit together like a jigsaw puzzle. Likewise, we see that with the Australian bight. Notice the south part of Australia is kind of curved like that. The curve actually fits where Antarctica split off. We can actually trace through the interior movements of the Earth where the continents were for the past 2.5 billion years. So that's actually how we can establish this ice age cycle, or pardon me, this supercontinent cycle, where the continents come together, split apart, come together, and split apart. We know, for example, a detailed history of the growth of the continental land masses. In fact, I just put up an article on June 11th. The June 11th, Today's New Reason to Believe, talks about how just before the first oxygenation event, the continents covered less than 2% of the surface of the Earth. The oxygenation event jumped that up to 27% in just a few million years. Oxygen plays a key role in the buildup of the continental land masses. And so we can actually trace in detail the oxygen history of the Earth through taking isotope measurements and dating the time of when those took place. If you want the details, I put them in Improbable Planet, and in that book, I always give you a link right to the research papers that I'm citing, so you can read the research papers for yourself. You say, I'm not sure I'm competent enough to read those papers. Good news is this. Every science research paper, they publish an abstract where they give you the bottom line. And the abstracts by law are free to the public. You don't have to pay for them. Often you've got to pay $20 to read the whole paper, but you can always read the abstract for free. And we always give you a link right to that abstract.
Right up here. Yeah.
Getting back to our present-day belief or disbelief of climate change, is there anything that we can do to, from what you're saying, it's going to go whatever way it goes, even if we take reasonable actions to stop the warming effect? Is this true? Is there some practicality in what you're saying that we can do now?
Sure. Just 1 week ago, I finished my next book. It won't come out for a few more months. But the book basically addresses your question. Because there's a lot of material being published making the point that human activity is warming the planet And unless we make draconian economic sacrifices, we're going to be in big trouble. Now, that's kind of the Al Gore approach. He wrote a book and did a movie called An Inconvenient Truth. I'm trying to get a title past her editors. I'm not sure I'm going to make it, but the title I want for my book is A Very Convenient Truth. We've had this amazing period of climate stability, and we got the wherewithal to sustain that climate stability for at least another 1,000 years, maybe even longer, and we can do it without draconian economic sacrifices. And so I got several chapters in the book where I talk about how we live on a planet that's been designed by our Creator. So when we face issues in obeying the command that He gave us in Job and Genesis to manage the planet for your benefit and the benefit of all life. It's crucial we see both those points, our benefit and the benefit of all life, which implies there will be solutions to our ecological and environmental crises that will benefit us and benefit all the rest of life on the planet at the same time. So basically what I'm doing in this book is basically encouraging us, exhorting us to look for those solutions. And I actually give a couple of dozen such solutions in the book, which would actually restore climate stability and at the same time boost the world economy. Democrats are going to love it, Republicans are going to love it. Who's going to vote against a solution that basically improves the environment, stabilizes the climate, and puts more money in everybody's pockets? I'll give you a couple of examples. Okay, we have made the Sahara Desert 10 times bigger than what it was in the days of the Roman Empire. What we could do, and the reason why it's so much bigger, people on the south edge of the Sahara Desert have been stripping that edge of vegetation for cooking fuel. And during the 1960s and 70s, the Sahara Desert was moving south at a rate of 6 miles per year because of people stripping the land of vegetation. What we could do is go to those sub-Saharan populations and say, we're going to give you all the kerosene you want, free of charge, use it any way you want, on the condition you work with us to replant the Sahara Desert and bring it back to what it was during the Roman Empire, or what is now the Sahara Desert, fed Europe with grain. Okay, if we could replant the Sahara Desert, that would give an income for all those North African peoples, and it would soak up huge quantities of greenhouse gases. Who's not going to want it? How quickly could that be done? It could be done in less than a generation and a half. It could also be done with the Gobi Desert. The other thing we could do is restore the whale populations. This has just been newly discovered. In fact, one of these papers was just published 2 months ago. How whales fertilize the photic zone of the ocean. And 70% of the life on planet Earth that pulls greenhouse gases out of the atmosphere are the phytoplankton in the oceans. Whales fertilize those phytoplankton, and they're the only creatures that do. So if we can bring the whale population back up to where it was before the pre-whaling days, that would mean we'd have an increased population of phytoplankton, which would give us an increased population of zooplankton, which would give us an increased population of fish, which gives an increased population of giant squid. And by the way, that's how they discovered this. Sperm whales are beginning to recover. Sperm whales only eat giant squid. But what they noticed is with the return of the sperm whales, we got more giant squid and they're bigger. They said, how could this be? They only have one predator, the sperm whales. But what they discovered is sperm whales fertilize the phytoplankton, which makes more zooplankton, which makes for more fish, which means the giant squid have got more food to eat, which explains why we got more giant squid and we got bigger body sizes for the giant squid. And so what this means for human beings is that we have a shortage of fish in the oceans today. We could restore the fish population, which means there'd be more income and there'd be a healthier diet for the world's people. And at the same time, we pull huge quantities of greenhouse gases out of the atmosphere. If you want another 2 dozen, wait a few months and the book will be out. I do have 4 of those in the book Improbable Planet.
All right, we think we have time for 2 or 3 questions. Let's start right over here.
I was interested in knowing there was another cataclysmic event when the dinosaurs died.
Yes.
According to that, that was the reason they died was because, again, the clouds covered the earth,
Right.
particulate matter, the whole thing. What I'm curious about is the dinosaurs were huge. We never had anything as huge except perhaps the mammoths that followed.
Right.
But even they were in no. What was the constitution of the air that permitted such a huge? Would we have been able to live at the same time?
Well, the oxygen content was roughly the same as it is now. The reason why you have these huge land animals on the face of the earth, that was a time when the continents were covered with these huge shallow seas. So half of North America was a huge shallow sea. Same thing was true, well, about a third of South America and a lot of Asia was covered with these shallow seas, which means that for the first time it was possible for the Creator to create really big land animals, because now you had the water to provide the buoyancy to support that high body mass. The biggest animal on the face of the earth today, a land animal, is an elephant. And that's at the limit that the laws of physics will tolerate. If you make a land mammal any bigger without water support, that animal will injure itself quickly because of the law of gravity. I mean, you see that watching the NBA. Who are the players that get the greatest number and most devastating injuries? It's the guys that are 7.5 feet tall and weigh 300 pounds. The law of gravity basically has its consequences. There's an advantage to not being tall. When you fall, you don't hurt yourself so much. Well, the same principle happens with land animals. However, if you've got, say, 15 feet of water, that water now provides enough buoyancy that you can have a land animal that weighs 50 tons. Whereas without water buoyancy, your limit is about 6 tons, like you see with the elephants or the mastodons. And it's a principle you see in Psalm 104, how God packs the planet with as much life as possible, as diverse as possible, basically making the point, when the geography is different, you're going to have different animals. And so with shallow seas, yeah, now you can pack the planet with really big land animals, namely the dinosaurs. And what's interesting, the biggest dinosaurs we see during the dinosaur years are at the limit of what the laws of physics will tolerate. You can't have bigger dinosaurs than we actually see in the fossil record. But they can only have them there when you've got these large shallow seas to provide the water buoyancy that they need to prevent themselves from injuring themselves. It explains why the biggest animal that has ever existed is the blue whale. But the blue whale is 100% supported by water buoyancy.
Interesting. It explains a lot of my personal problems. All right. Right, question right down here.
Can you explain a little bit more about your faith convictions and how those intersect with your scientific explorations?
Yes. I was born, raised, and educated in Canada. Where I lived, there were no believers. But I became interested in astronomy when I was 7. And I was actually reading 5 books on physics and astronomy per week. I'm on the autistic spectrum. Those of us in the autistic spectrum kind of behave like that. We're natural nerds. But it was my astronomy that persuaded me Big Bang cosmology really explains the origin and history of the universe. And it was Big Bang cosmology that means the universe has a beginning. So starting at age 17, I began to search for that cosmic beginner. The first place I looked was in the writings of Immanuel Kant and René Descartes, because those were the European philosophers that wrote the most about cosmology. But I discovered they had the wrong concepts of space and time. And so I began to look at the different holy books that undergird the religions of the world and began to test them with what I knew to be true from geography, science, and history. And I was able to quickly go through, Hindu Vedas is where I started first. And they talk about an oscillating universe, a reincarnating universe, and where it reincarnates with a cycle of 4.32 billion years. I recognized the number was wrong, and also they were wrong about the entropy of the universe. About a year later, I picked up a Gideon Bible and began to go through that and realized it got all the science 100% right, and was the only book that predicted future scientific discoveries. What astounded me is that it actually predicted that we live in an expanding universe with a space-time beginning, where the laws of physics never change, and where one of those laws is a pervasive law of decay, which implies we must be living in a universe that gets colder and colder at a highly predictable rate. And that particularly what impressed me, astronomers began to develop the capability to measure the past temperature of the universe at different epochs, all the way back to 13 billion years ago. And those temperature measurements perfectly fit what the Bible predicted thousands of years ago. And also seeing how the Bible predicted future historical events. And so that persuaded me this has to be a communication from the one that actually created and designed the universe for our benefit. And so after studying a Gideon Bible for 2 years, the Gideons have a place where you can sign your name, where you commit your life to make the Creator the master of your life, and to receive His offer of redemption from the evil that surrounds us. And I said, that sounds like a really good deal. So I signed my name in that book. But ever since then, I've found a perfect fit between the book of nature and the book of Scripture. And so Reasons to Believe is an organization I founded basically to test different faith beliefs. Because what we see in the Bible is a statement that the more we learn about nature, the more evidence we'll find for the supernatural handiwork of the Creator. And so that's why I produce a blog every week giving you that increasing evidence, and why on my Twitter page I give you links at a rate of about 3 research papers a day that give us more evidence for the Christian faith and the reliability of the Bible. The Bible commands us to objectively test every belief. And so we're basically demonstrating that through the book of nature. It's a tool God gave us to test our belief systems.
Thank you. One last question. I know it's running a little late, but just hang with us. Go ahead.
Thank you very much for an interesting lecture. You talked about all this creation stuff, but when did man come? Did he evolve as an ape? Did he evolve from one of these other creatures? And how do you know that there isn't some other kind of life form that's starting now as we started?
Okay, those are good questions. And one of the books that you can get at Reasons to Believe is on human origins. It's a 400-page book, so it's quite detailed, answering those kinds of questions. But this is an area where we need to do interdisciplinary work. And so one of the things we've noticed, for example, is when humans were first here about 100,000 years ago, or 50 to 100,000, there were over 8,000 mammal species on the face of the earth. Today, there's only 4,000. Half of them have gone extinct. During that human period, we've not seen the appearance of a single mammal species. So the extinction rate has eliminated half of them. The replacement rate is 0. This led conservation biologists to do field studies. What's going on with these mammals? And many field experiments basically demonstrate that with a terrestrial land mammal with an adult body size less than 3 kilograms, that is less than 7 pounds, it goes extinct before it can evolve into a different mammal species. Now, there's a dozen different species of bipedal primates that precede human beings that have been discovered. In fact, one of them was published in the British journal Nature just yesterday. You can read about it, brand new species that they have found. They all have adult body sizes bigger than 7 pounds, which means they're not going to evolve one into the other. And it was Ian Tattersall who communicated to us at Reasons to Believe. Ian Tattersall is an anthropologist who's an atheist, but he was the one that pointed out to us, notice these bipedal primate species are limited to Europe, Asia, and Africa. We've yet to find fossils on North America, South America, or Australia. So the other thing you notice is that when humans moved into Australia, they quickly drove to extinction 94% of the large-bodied bird and mammal species that lived there, and hence they never got out of the Stone Age. They killed off all the animals they needed for civilization. They killed off the horses, the camels, the sheep. They were all killed off. And to not quite to the same degree, the same thing happened in North and South America. South America, the extinction rate was 79%. North America, 73%. Africa has 10 of those dozen species. The extinction rate when humans entered Africa was only 4.5%. And it was Ian Tattersall who said, when you actually look at these bipedal primate species that precede humans, the cranial capacity goes up and down. It's not this linear evolutionary pattern where the cranial capacity gets bigger and bigger with respect to time. It goes up, then it goes down, it goes up, it goes down. Likewise, the bipedal capability goes up and down. There is no linear progression. And his comment is every time we find a new fossil of a bipedal primate, it throws our evolutionary models into chaos. And a good example of that is what got published on Wednesday in the British journal Nature. Again, it's throwing everything into chaos. But he says the one thing that fits, as you look at this sequence over the past 6 million years, we see that these bipedal primates are progressively more capable in hunting large-bodied bird and mammal species. And for example, the Neanderthals that preceded us, it seems like they exclusively survived on the meat of large-bodied bird and mammal species. And it was Ian Tattersall who says, I think what was going on is these animals were step-by-step trained. When you see big animals walking on 2 feet with weapons in their hands, run. And so what we see is a survival rate that's very high in Africa and a survival rate that was extreme in Australia. But one had the bipedal primates, the other one didn't. And what makes us human beings unique, we're the one bipedal primate that's got symbolic capability. We're the one bipedal primate where the technology advances. What we see with Neanderthals, the technology was limited to shaping single stones. And the technology at the beginning of the Neanderthals on the face of the earth is the same as at the end. And in every case, these bipedal primates, with the exception of us human beings, can't figure out what a stop sign means or a railway crossing, can't make a number system, no mathematical capability, and they don't have an alphabet. They're not able to communicate with a large vocabulary. As we see with humans, even very young humans, they develop a large vocabulary quickly, and they just seem to have an innate capacity for symbolic facility. I think one of the more dramatic examples of that is put a computer in front of a 9-month-old child and see how quickly they pick up that symbolic capability. It's utterly amazing how quickly they pick it up. But that's unique to human beings. We don't see it in any non-human animal. And the other interesting thing is there's a paper published in Science, and it was titled Darwin's Mistake. And it was basically making the point that Darwin said, if my model is correct, the animal that's most similar to us physically will also be the most similar to us intellectually. And so he was predicting that the chimpanzee would be the smartest of the non-human animals. And he encouraged people 170 years ago to put his claim to the test. No one did until 9 years ago. It's the first time anyone ever did an experiment to test his claim. And that experiment basically points out chimpanzees are not the smartest non-human animals. Crows and ravens are the smartest non-human animals. And so when you say that someone is a bird brain, it may be a compliment.
Well, thank you very much. Thank you to each of you for coming. We left a little bit longer today. I hope you appreciated that. Dr. Ross will be down here at the front if you want to talk with him. We really appreciate it. See, not next week, no meeting next week. Come back in 2 weeks for Martha Barnett. Thank you so much.